Hello, everyone. Before we start today's lecture, let's review the contents in the last class first. In the last class, we actually defined a similarity measure based on the information theory. Information theory is quite an important concept if you are interested in the data analysis. So, we actually the mutual information here is one of the popular similarity measure based on the information theory. And the information theory also provides some other important concepts in machine learning or data analysis. If you are interested in, oops, if you are interested in maybe some classification, then your loss function or cost function can be cross entropy, which is one of the most widely used loss function for regular classification. So before we see the mutual information and cross entropy or other things, we first define the information, the concept of information, and the amount of information. So in the last class, we mentioned the definition of information. The information is the possible outcomes of an event. So if we flip a coin, then the outcome will be either head or tail. Then knowing this result is information. That actually coincides our common sense or the world usage in the real life. If we have information, it means that if we know something. Actually, here information theory, if we have information, it means that we know the result of an event. Okay, so that is the definition of information. So transmission of message, flip a coin, and a measurement of a piece of data, they can all be the information. However, the amount of information may not be the same for all kinds of cases. For example, if we flip a coin that only has two heads, it means that the result will be head with 100%. Then in this case, we already know the result of this event, which is head, before we flip a coin. So in this case, if we observe the result of flip of coin, may not give any information to us because we already know the result of this coin toss before actually it is tossed. And let's see another case. Okay, the amount of information. Okay, let's see this example. If we have a coin, and after we flip a coin, the probability that it will give head is 99% and it will be tail with 1%. then before we toss a coin, we or most people can expect the result will be head, okay, because it has much higher probability than the probability of tail. And let's assume that we actually toast and observe the result of the outcome, and the outcome is head. Then it will give some information. However, it will not give much information because most people expect it'll be head. Okay. So if the result of the coin toss is head, then it will give not that much information. However, if the result is tail, then the people will be surprised with this event because the out the outcome only with the 1% actually occurs. So in this case, knowing the result of this coin toss is tail is maybe it is much valuable than the knowing the result of head, and we define that this surprise gives us much information. So in this case, we can say that the result of tail can provide much more information than the result of head. So we define the amount of information as inversely related to the probability of an outcome. So if we can define amount of information as 1 over pi, however, if however we take log here because let's assume that the probability of 1, which does not give any information, if we take log here, then probability 1 gives the 0 information. However, if we do not have log here, then the probability of 1 gives information 1. So it's just difference of the definition. However, it's more natural to us that 0 no information has the 0 value of amount information. So we define the log 1 over pi as the amount of information, and it is actually log minus log pi. Okay. And the entropy is the most, I think, in my personal opinion, it is the most important concept in the information theory. It is the expected amount of information that of an event if we know the result of the event. Okay. So there is an event X, for example, the coin toss, and we have n possible values x1 through xn, and we have corresponding probabilities. Then the entropy of X is defined as the expected amount of information that in the case that we observe the result of this event. So here the entropy is defined as the expected amount of information, and it can be written as the weighted sum of the probability and amount of information of each outcome. And if we substitute this AIXI as minus log pi, then we will get the entropy as minus summation pi log pi. And we also, in the last class, we also mentioned the base of this log if the base of log is 2, then the unit of amount information is, we call it as bit. Okay. However, the base of log is the natural constant E, then the unit of this entropy becomes net. So in data analysis or computer science or related society, the unit of entropy is usually a bit. It means that we usually use 2 as the base of this log. However, if you see the concept of entropy in physics textbook or some natural science context, then it may be the mm, the base of log may be the natural number e, so the unit of this information would be net. So in our class and actually in our department, we will use 2 as the base of the log. So in that case, the entropy has the values between 0 and log 2n. So for the value 0, this case means that one of the probability is 1 and the others are all zeros. So in this case, we know the result of this event before we observe its real outcome. So so in this case, this event will not provide any information, so the amount of information, expected amount of information, the entropy is 0. And it will have the value of log n when the all probabilities have the same value, 1 over n. Okay. And we saw the entropy example. We calculated the coin toss and a fair four-sided die. Maybe you can calculate the entropy of a fair six-sided die or whatever. I think it is not that difficult to calculate the entropy by yourself. And we saw how we can calculate the entropy with the samples. Instead of the probability, then we can use the sample frequency here to calculate the entropy. And we define the mutual information here. The mutual information is the information that one variable provides about another. So if we have two variables x and y, the mutual information means that how okay, if we observe x, then how much information that we get on y, okay? It, in other words, how much of information of y the x contains, okay? How much x contains how much information on y and vice versa. They have two values. The mutual information between x and y and x are the same. So the mutual information function is a symmetric function, and in in other words, the mutual information means that if we observe y, then how much of information that we get on x. Okay. So this mutual information can be defined as here. For example, one definition is the hy minus hy over x. It means that hy is the expected information that we observe the result of y, and hy given x, we call this one as the conditional entropy. I already wrote it in the last class. The conditional entropy here. The definition of the conditional entropy is written here. The definition of conditional entropy is that if we already know x, then what is the expected amount of information that we get when we know the result of y, we observe the result of y. So this part means that the amount of information of y that is not explained from x. Information of y that is not explained by x. So their difference is actually the expected information of y that can be explained by x. Okay. Here's the information of y, and here's the information of x, and this part is mutual information of I, x, and y, which means that if we know x here, then we know y with this amount of y. Okay, and okay, I want to draw it larger. Okay, here. I will draw the Venn diagram for the mutual information here. Okay, this is the, let's assume that this is the information set of x. This is the I'm not good at drawing circle. This is the information set of y. Okay, actually, we want to calculate this amount. This is actually the mutual information of x and y, and here. So if the mutual information is high or large, it means that x and y has a lot of similarity, and if it is low, it means that the x and y does not have that similarity. They may be different. Okay. And okay, to calculate this part, we have two ways. The first one, let's assume that the area A, B, and C. So C is the mutual information. We have to calculate C, we have two choices. The first one is A plus C minus C. Okay. Of A plus C minus A. And it is also the B plus C minus B. Okay. And we know A plus C is the entropy of X, the expected amount of information of X, and B plus C is entropy of Y. Then we written as A as the H X given Y. It means that the information on X that is not explained by Y. So this conditional entropy is here. If we already know Y, actually the A part. If we already know Y, then what is the new surprise? Then we observe X. Okay. So this h x given y is A, and B is h y given x. Okay. So the mutual information can be written as here. Okay. Written written like of here. The mutual information I x comma y is the hy minus h y given x and hx minus h x given y, and it can be also calculated like this: hx plus hy minus hxy. So in this Venn diagram, we can say the a plus b plus c as h x comma y. So c can be calculated as a plus b plus c. Oops, sorry. A plus c plus b plus c minus a plus b plus c in this way. Okay. So the concept of this way is here. Ixy is can be calculated as hx, hy, hxy. Hxy is the joint entropy of x and y. So if we know this one, we all know the information of x and y jointly. Okay. I'm not sure that I correctly explained the concept of mutual information in the last class. However, if I made some confusion for the mutual information in the last class, I apologize. But when what I mentioned today is correct. Okay, here, this one is the definition of conditional entropy. Okay. And for discrete variable, it is easily calculated. However, for the continuous variables, we can make binings, and we can compute the mutual information with these bins and normalize the log to minimum of nx and then y and take the highest value. Okay. And we also saw the way of combining similarities. We have first the indicator delta that this symmetry this similarity for this attribute will be used or not. And also we can give the weight to the similarities. If we do not want to treat all attributes the same, if we want to make some differences on the attributes, then we can use the weight and make the weighted average for the similarity for each attribute. However, there are so many ways to make the combination of the similarity of each attribute so that we make the total similarity. So this is just one example, and you can choose any other way to combine your similarities. Okay. And okay, today we will see the last part of chapter 1. Wow, chapter 1 was really long. This is actually, I hope this is the last class for the chapter 1. In the last part of chapter 1, we will see the data preprocessing, aggregation, sampling, discretization, and binarization, attribute transformation, dimensionality reduction, feature subset selection, feature creation. And okay, data preprocessing means that the we handle or manipulate have the bad meaning. So um, we process or we give some calculation to the data before we analyze or apply the analysis method to the data, because because of preventing some failure in the data analysis procedure. Okay, so for the data analysis, some people said that data preprocessing is actually 80% of work of data analysis when given data. So data preprocessing is really important, that when we analyze the real data and in other words, if you see the data that you need to analyze, then please do not apply your data analysis method directly, but first you need to apply the appropriate data preprocessing method to your data. So the first one is the aggregation. The aggregation is combining two or more attributes or objects into a single attribute or object. So because we combine two or more attributes into a single one, the data size of data will be reduced. So if we combine attributes, then the number of attributes will be reduced. And if we combine objects, then the number of objects will be reduced. And it is also widely used when we change our scales. So for example, the days can be aggregated into weeks, months, or year. For example, we have daily data. However, we want to change it to the weekly data, and one of the easiest way is just summing all the attribute values of daily data by each week. So that is the actually aggregation. And if we aggregate these scales, then we will get the more stable data, because the aggregation of the data tends to have less variability. Because if there are noise on data, if we aggregate some data, then the noise of each data can be cancelled out. So if we aggregate some data or some attributes, then we will get more stable data. So here's the example, the precipitation in Australia. So here the word precipitation means the amount of rainfall. Okay. So this example is based on the precipitation in Australia from the period of 1982 to 1993. So we will see these two histograms. Okay, the first one, oops. The first one is the, okay, here's the Australia. Australia is divided into by the 0.5 degree grid cells, and we have total 3030 these cells in the Australia. And the first histogram is the standard deviation of average monthly precipitation, and the second histogram is the standard deviation of average yearly annual precipitation. So the monthly data is aggregated to the yearly data, and we will compare their standard deviation. So high standard deviation means that the variability of the data is high, and the low standard deviation means that it's less variable. So here we can see that the standard deviation of the average monthly precipitation, the histogram on the left has higher variability compared to the right one. So as we mentioned, if we aggregate the monthly data to the yearly data, then we will get more robust data for this example. Okay. If we use shorter scale data, for example, weekly precipitation or daily precipitation, then maybe get more variable data or more variable histogram than the first one here. And the next one is the sampling. Sampling is the main technique employed for data reduction. So it is often used for both the preliminary investigation of data and the final data analysis. So if we want to observe the characteristics of data, and if the number of data is too large so that we cannot analyze all the data easily, then we usually use sampling. It means that we pick some samples from the data and only observe these data to find or estimate the characteristic of the original data. We are very familiar with this concept, okay? We use this sampling concept in so many cases in our real life. In statistics, the sampling, the main reason for sampling is to obtain the entire set of data is too expensive or time consuming. In other words, if we want to know the average height of, of all people in Korea, then to get this value, it means that we need to check all the heights of all the people in Korea and take the average. However, we know how can we know that we do not calculate the average height in this way. We sample some people which can represent the group, maybe each group of people, and then take height only for only these samples and take the average of these samples, and we expect the average height of the all people in Korea with this sample average. So if you took some statistics class you are, I guess, you are familiar with this estimate concept here. Here's the total dataset. In statistics, it is usually called the population. In Korean, 모집단. Population. And to estimate the characteristics of population such as average, standard deviation, and blah blah blah, we make sample, very small subset of this population, but this sample should be able to represent the population. And we find the characteristics of that we want, not in the population rather than the sample. And then with this sample characteristic, we estimate the population of V, and yeah, this here at the estimation means that we use some confidence intervals or that kind of things. So the sampling is used in this way in statistics. However, in data mining, data analysis, sampling is typically used because the processing of entire set of data is too expensive or time consuming. In the data analysis, the total data set is usually given. However, well, uh, as I mentioned earlier, it is sometimes time consuming and it's too expensive to process all the data set is quite sophisticated. Then we just take some samples and find the characteristics. So if the sample is representative, it means that it can represent the entire data set, then using a sample will work almost as well as using the entire data set. So in other words, if the sample is representative, and then we can use sample instead of the entire data set. Here, a sample is representative if it has approximately the same properties as the original set of data. Okay, so in this case, then we can use the samples instead of the original entire data. However, it depends on the sampling size. Okay, let's assume that the figure in the left is the original data set, and here's our samples. The case is that we sample 2,000 points and only 500 points. So if we see the original figure, we can find maybe there are three kinds of data points. The first one is the data points included in these or these large clusters. Okay, and the second type of the data points is the data points which consist, which compose this sine wave. The sine wave. Okay, I think you can easily find the sine wave in this data set here. And the third type, the last type of data is the others, maybe the noise. If we sample 2,000 data points, we can easily see. Oops. Oh, sorry. Um, Okay. If you see the figure in the center, which is the result of the 2,000 point sample, you can see there are data sets in the large clusters, and you can see the sine waves here, maybe. And there are some noise data point. However, if we reduce the sample size more to the 500 points, you cannot see, maybe you cannot easily find the sine waves here. Actually, I can't find any sine waves here. Okay, so if you reduce the number of data points too much, then you may lose the properties of the original data set. Okay. And there are many types of sampling. However, in this page, we will only see two types of sampling. The first one is the simple random sampling. It is, you can easily guess what is the simple random sampling from its name. We put the equal probability of selecting to the all instances in the original data set, and sampling. There are two random sampling. The first one is the simple sampling without replacement. So it means that if each item is selected, it is removed from the population, and in other words, it is not selected again. Okay, only one each item can be selected only once at most. However, the sampling with replacement means that the objects are not removed from the population even if they are selected for the sample. Okay. So in this case, one object can be selected as many as possible. Okay. So I think maybe we have 1, 2, 3, 4, 5, and we sample 3 numbers. If we sample without replacement, then the sample may be 2, 5, 3. We will see in. Okay. If we select 2 first, then 2 is removed from the population, and the next sample is drawn from 1, 3, 4, or 5. And if we sample 5, and 5 is also removed from the population, and here this position will be drawn from 1, 3, and 4. However, if we sample with replacement, if we selected 2, then this position can be selected from all of 1 through 5, so 2 can be selected again. Okay. So I think you all know the sampling with replacement and without replacement. We usually sampling without replacement. We usually use this one more than the sampling with replacement. However, in data analysis, sampling with replacement sometimes important because it is used some concept that bootstrap or bootstrapping. And another type of sampling is the stratified sampling. Stratified sampling is that split the data into several partitions and draw random samples from each partition. So stratified in Korean, 층별. So it means that if in the population there are two distinct groups of the data points, if we, okay, this is the population. If we make sample from the, okay, let's assume that if we take 4 samples and they have equal sizes, then this sampling can be drawn if we do not have lock. Only from one group over here, or 3 from here, 1 from here, and that is not, then this sample will not have the same characteristic with this population. However, if we use this stratified sampling, it means that we first analyze, oh, we have 2 groups of population and they have the same, well, almost the same weight, same numbers, then we will sample the same number of samples from each group. So we will sample 2 from here and 2 from here manually. And 2 from here randomly and 2 from here randomly. So we can get 2 data points from group A and 2 data points from group B. And this kinds of the sampling is called the stratified sampling. We first analyze the groups or partitions in the population or entire data set, and we use the sampling from each group to ensure the sample has basically the similar characteristics of the population. And here are interesting questions. What sample size is necessary to get at least one object from each of 10 equal size groups? Here we have 10 groups. We have 10 groups, and we will randomly sample from the population, and population has 10 groups. And what is the probability that at least one object is from each of 10 groups? So the minimum number of sample size that satisfy this condition is 10, of course. If we sample less than 10, we cannot satisfy this condition. However, if we sample only 10 data points, then it is very less probable that the objects in every group are selected. So that is the answer for this question. If we sample only 10 samples, 10 instances, then the probability is almost 0. However, if we sample maybe 27, 28, then the probability is just over the half. And if we sample 60 or 70 instances, then the possibility becomes 1. However, this is the case for the random sampling. If we use the stratified sampling, then if we sample 10 data points, then we manually select each data point from each group. So if we know the population is composed of several groups, then stratified sampling is maybe more appropriate than the random sampling. And the next concept is discretization. Discretization is the way that changing continuous variable into the discrete variable, especially the original attribute. If we handle the continuous variable, it means that there are potentially infinite number of values that can be taken from this attribute. So let's see this figure. We only need to consider the x-axis. That is the value of the continuous attribute, and the vertical axis is uh, just given any random number from 0 to 1, so that we can easily see the all data points. So we have many values here for this attribute, and here, and here, and here, and we have two outliers, 0 and 20. Okay, so the question is that if when we want to discretize this attribute, what is the good boundaries for the attribute values, and how can we find it? We know the answer, maybe. It seems that here, maybe here, like this. This discretization may be good because there are some groups here. However, how can we find these boundaries? If the easiest way and very naive way is to make the equal interval with to obtain four values, for example, because the minimum value of this attribute is 0 and the maximum value is 20, so we make the intervals that has the 5, that has each interval has the length 5. We can see it is not appropriate for this case that our information, I mean our example. However, this, so you may get some intuition that this discretization, I mean the equal interval discretization, is not good. However, it is really widely used in the real data analysis. Even though it is not appropriate, they do not validate or examine whether it is good or not for the data set that they try to analyze. However, so if you, what I want to mention is that if you want to make some discretization, then first you need to understand the distribution of your data attribute values. Maybe you can also make discretization with equal frequency so that each interval has the same number of data instances. It is also really, really commonly used for the discretization. If these two discretization may work if the attributes are uniformly distributed. However, if the attribute values are grouped, such as our example here, then maybe we can use the clustering. So because we do not deal with any clustering method, so you don't need to care about this clustering method. However, if you can find the groups in the attribute values, then you can make much better discretization boundaries. And I will pass this supervised discretization. And this binarization is changing a continuous or categorical variable into one or more binary variables. Okay, for example, here, it is really widely used to changing categorical variable into binary variables or one hot vector. Okay, this is the example. If you have 5 values of poor, okay, good, and great, then if because you have these 5 values, then changing into the binary variables, then make 5 dummy variables from x1 to x5, and the first category awful at 10000 and poor 01000, okay 00100, good and great, like this. And these vectors are called one hot vectors because all elements are 0 and only one element is 1 in this vector. Only one vector is hot, on. So this vector is called one hot vector. And these attributes composing one hot vector are called usually dummy variables. This one hot encoding, we call this binarization sometimes as one hot encoding. And this one hot encoding is really convenient because if you changing your categorical variable into these binary attributes, then you can apply any mathematical calculation, add some, okay, make finding the distances, multiplying some values. So you can apply your data analysis method that only can handle the numerical values. So then in that case, the categorical values, if you change these categorical values into these one hot vector, then you can apply your method. You have more freedom, more options to choose the data analysis method. So this is actually not the requirement. This is actually the mandatory and mandatory in the recent data analysis society. And the next one is the attribute transform. Attribute transform is a function that, here's the, it's a function that maps the entire set of values of a given attribute to a new set of replacement values such that each old value can be identified with one of new values. So maybe it can be changed by the simple functions. X is changed into x to the k, and or log x, or e to the x, or absolute value of x, or sometimes two values, x and y, transformed into two values, x plus y or x minus y, whatever. When this new attribute has more meanings, are more meaningful than the original attribute. one of the most important attribute transform is the normalization. The normalization that we slightly mentioned, this normalization when we talk about distances. Sometimes one attribute has a large values and one attribute has small values if they have different scales. So then the Euclidean distance is dominated by the large scale attribute. That is the limitation of the Euclidean distances or the Minkowski distances that we mentioned earlier. In that case, we I'm sorry, we need to use the normalization to handle this problem. The typical normalization, the famous ones, are the z-score normalization. Here's the attribute. Okay, let's say that x tilde is new attribute, then xi is the original attribute, then z-score normalization is the subtracting mean of each attribute from the attribute values and divide it to its standard deviation. So it's kind of standardization of normalization. Okay. And min max scaling. So in this case, xi is defined as xi minus x minimum and x max to x minimum. So it means that transformed the attribute values, the minimum attribute value to the 0 and the maximum attribute value to the 1, and the others will be located between 0 and 1. Okay. This one is min max scaling, so minimum value will be transformed into 0 and the maximum value will be transformed into 1. So these two are, I think, most popular normalization methods, and there are so many variants of this normalization, so you can use any one that you want, or with the one that is proper to your data. Anyway, so if you use this normalization, then you can adjust to differences among attributes. And sometimes this normalization is applied for the seasonality. We will see the example in the next page. So here, this standardization means this one. Okay. So this one is the sample time series of plant growth. Okay, this graph is net primary production is a measure of plant growth used by ecosystem scientists. So this graph shows the plant time series of plant growth in 3 places. The first one is the Minneapolis, and the second one is Atlanta, and the last one is Sao Paulo. So here, if you see that, if you see this graph and if you find the correlation between these time series, there are a lot correlated, both positively or negatively. They seems to correlated a lot. However, if you normalize using monthly z-score, it means that subtract monthly average and divide by the monthly standard deviation, then correlations are very low. It means that they are almost independent. We know why this similarity, we know why these correlations are high because there are seasonality. The plants grow a lot in summer and they do not grow that much in winter. So Minneapolis and Atlanta located in northern half of the Earth, so that the summer is maybe June, July, August, and in this season the plants grow a lot. However, Sao Paulo is locating the southern half of the Earth, so maybe their summer is December, January, February, so they then the plant will grow these days a lot. So these related patterns are just because of the seasonality, the actual seasonality from the seasons. So if we remove the seasonalities here, then we cannot find that their plant growths are mostly independent. And the next topic is the curse of dimensionality. This is the important concept. You need to remember this. The curse of dimensionality is that here, when dimensionality increases, the number of instant attributes increases, then the data becomes increasingly sparse in the space that it occupies. And in this case, the definitions of density or distances between points become less meaningful. If you see this graph, when we generate 500 random points, when the number of dimension is 2, then the distance between the maximum distance and minimum distance divided by the minimum distance is 3 something. So here's the log 10. It is almost, for example, more than 1,000. However, the number of dimensions becomes higher, then this graph go downward. It means that the difference between maximum distance and minimum distance becomes low. So it means that all the distances becomes almost the same if we increase the dimensions of our data set. The reason is here data becomes increasing sparse in the space that it occupies. If the dimension is 1 dimension, there are a lot of data are very coarsely located. However, dimension is 2, then data are sparse, and dimension is 3, data are more sparse, and blah blah blah. Okay. So if however, the densities or distances dissimilarities are really important concept to analyze our data, especially for clustering, outlier detection, and many other data analysis methods. So it means that they may not properly work on high dimensional data set. So to overcome this limitation, a simple way is to reduce the dimensions of the data. So if we reduce the dimensions, we can avoid the curse of dimensionality. Okay, not curse. And we can reduce the amount of time and memory required by data mining algorithm because the number of attributes are reduced, and allow data to be more easily visualized, especially we reduce the attribute to 2 or 3, and it may help to eliminate irrelevant features or reduce the noise. We will not deal with the specific ways in this chapter. However, one of the famous one is the PCA, Principal Component Analysis. The goal is find a projection that captures the largest amount of variations in the dataset. So here, here are data points that we have it. They are located in 2 dimensions, x1 and x2. However, if we want to reduce these 2-dimensional data sets into 1 dimension, then we need to find an axis that can represent this data as much as possible, and that the result is this E, so that in this 1-dimensional axis, the data are located like this. They are projected into this. So with these dimensions, with this axis, the dataset can be represented into 1 dimension. That is the main idea of PCA. I think we may not cover this algorithm in this semester. Maybe you can see this algorithm in other statistics class or maybe other data mining or machine learning class. Okay. And the next one is a feature subset selection. It is another way to reduce the dimensionality of data. It means that there are actually the many attributes and just select a few of them. So in feature subset selection, we want to eliminate the redundant features. Redundant features mean duplicate much or all the information contained in one or more other attributes. In other words, these 2 attributes gives similar or the same information, then they are called redundant, and we need to eliminate one of them. That means the redundant features. And the irrelevant features means that containing no information that is useful for data mining task at the hand. So irrelevant features, for example, if there are some attributes that is not related to our task. So for example, if we want to make a task of predicting students' GPA grade, then the student ID is not relevant to the grading grading of the students. So we can eliminate this feature to predict for the task of prediction of the students' grades. There are so many subset selection techniques, so we will not go in detail. Maybe I'm not sure that you can see many algorithms in another class. And the next one is the feature creation. It means that create new attributes that can capture the important information in a dataset much more efficiently than the original attribute. For example, we can make feature extraction. So if we want to analyze the images, then sometimes it is useful that extracting the edges and use these edges, not the whole image which has the colors and a lot. And feature construction, if we have the mass and volume, then sometimes the density is more useful than mass and volume, so we divide mass by volume, then we can get the another attribute density. And this one is very specific, mapping data to new space Fourier or wavelength analysis. So here, the figure in the left-hand side is the sum of two sine waves and noise. However, we cannot analyze this data set because it is too noisy. It seems too noisy and we cannot find any two sine waves here. However, if we use the Fourier transform and make the frequency diagram as in the right hand side, then we can find two peaks. They are the frequencies of two sine waves and the others remaining very small. So if we use this kind of transformation, then we can find the characteristics or properties of data set more easily. Wow, this is the end of chapter 1. And finally, let's move on to next chapter in the next class. See you on the next class. Bye.